So in this lecture, we'll continue our discussion on statistical inference. In last lecture, we introduced the concept of hypothesis and demonstrate how to use hypothesis testing to validate whether or not a serial production process is in control. And we also discussed the advantage of using a sample mean to do the hypothesis test compared with using an individual box of cereal. And the advantage coming from this following law, which is if x follow a normal distribution, then the sample mean based on x follow also a normal distribution with the same mean but with a much smaller variance or a much smaller standard deviation. And with the knowledge of hypothesis testing, you know that a smaller standard deviation means a smaller beta and a higher power associated with the test. All the procedure we introduced in the last lecture are assuming that we know the precise value of the standard deviation of the process. But in reality, if we need to infer on the population mean, then it's unlikely that we would have the knowledge of the standard deviation. So in this lecture, we're going to focus on how do we conduct hypothesis testing for the mean without the knowledge of the standard deviation of the process. So a natural solution seems to be to replace the true standard deviation of the underlying process with the sample standard deviation, denoted as S. However, with such replacement, this quantity does not follow standard normal distribution, i.e. the Z distribution, exactly, especially for a small sample size. And the reason that it does not follow the normal distribution any longer is because the sample standard deviation tends to underestimate the true standard deviation for the process, and is especially so for a smaller sample size, such as the sample size we used in last lecture, which is measuring 25 boxes of cereals. By underestimation, it means that for a limited number of samples we draw, the sample standard deviation tends to be smaller than the actual value of the standard deviation of the process. So imagine what it would look like. Replace the true standard deviation with a smaller value, which is the sample standard deviation. Imagine how it would affect the density curve. So if S is smaller than the true value, which is sigma, then because the denominator is smaller, it means this quantity, the ratio, will be greater than its true value. And as a result, the whole density function will be more spread out than the standard normal distribution. And in the early 20th century, an Irish statistician named William Gossett actually proved this quantity with the true standard deviation replaced with the sample standard deviation follow a slightly different distribution from the Z distribution. It's called a T-distribution. So the biggest difference between the T-distribution with the Z-distribution is it has bigger tails on both ends. A second difference is there's only one standard normal distribution Z, but there are a sequence of T-distributions. And the reason is the following. Since the underestimation of S for sigma is because of small sample size, then the smaller the sample size, the bigger the underestimation. Therefore, the bigger the tails of the T-distribution. So in order to differentiate this sequence of T-distributions, we require one more parameters to differentiate them, and is called the degree of freedom, which is defined as n minus 1. N is the size of the sample you draw. So using our cereal box example, if we draw a sample of 25 boxes, then the degree of freedom will be 25 minus 1 equal to 24. This chart shows the sequence of T-distributions with different degree of freedoms. This curve in black is the standard normal Z-distribution. And as you can see that when the degree of freedom equal to 1, namely when the sample size equals 2, the yellow density curve is deviating more from the standard normal Z distribution with two bigger tails. And as the sample size increase, namely as the degree of freedom increase, the sequence of T distribution, the T density function, is gradually approaching to the standard normal Z distribution. A quick recap here. The T distribution is introduced to address the underestimation issue associated with a small sample size. And in fact, if you have a sample size that is greater than 120, the associated T distribution would almost exactly coincide with the standard Z distribution. So at which point then we can go back to use the Z distribution for hypothesis testing. So once we understand the reason why the T distribution was introduced, then to conduct hypothesis testing using T distribution follows the exact same procedure as applying the Z distribution. So the only difference is, again, just to use the degree of freedom to find the correct distribution. And by consulting with the T distribution table at the back of the textbook, you should be able to identify the critical values the same way we did before. So this diagram shows the comparison of using T distribution versus Z distribution for the cereal box example. So the information that is needed for the T distribution is listed here. So I'll leave this as a practice problem for you to figure out what the do not reject regions and the reject regions are, namely to figure out these two values for the sample mean. So we'll next look at a variant of hypothesis test called the Onetailed hypothesis test. We'll continue using the box cereal example. But now we have decided that we are not going to shut down the production line as long as the weight is not lighter than 368. In other words, customers will not complain if they receive a box of cereal that weight more than what is specified. If that assumption is valid, then we can set up the test this way. So the null hypothesis becomes mu greater than or equal to 368. And the alternative hypothesis, H1, becomes mu less than 368 grams. So under this new setup, the unlikely extreme observations become those that are located only at the left tail of the distribution. So by using the same logic, we could set the level of significance at 5%, based on which we should be able to find the critical value that corresponding to a position where to its left the probability represented by this shaded area is 5%. And so once you find the critical value, you can proceed to make the decision whether choose to reject or just do not reject a hypothesis. Now, which density curve you should choose to apply for the hypothesis test is dependent on whether the true standard deviation is known or unknown. So the similar idea for p-value also applies for the one-tailed hypothesis testing. Remember, the definition of p-value is given the null hypothesis is true. In this case, will be mu greater than or equal to 368. The probability of observing values that are more extreme than this particular observation. So in this case, if you make a measurement and you come up with 350 grams, then because this one-tail hypothesis, the value that are more extreme than 350 are those boxes that weigh less than 350 grams. So in this case, it becomes again one-tailed. So the p-value for the observation of 350 grams is represented by this shaded area. Again, this density curve again is dependent on whether you know the true standard deviation for the process, or you use the sample standard deviation to replace the true standard deviation. So based on those information, you will choose either the Z distribution or the T distribution with the proper degree of freedom. We are now moving on to discuss the second type of statistical inference, which is estimation. And the difference between estimation and hypothesis testing is, in hypothesis testing, we are making a claim that we need to use observation to validate. We make a claim such as mu equal to 368 grams for the cereal example. But in the estimation problem, we do not make such claim. Our goal instead is to try to estimate the probability distribution or the density function. So estimation problem is actually a much broader category than hypothesis testing. But in this lecture, we are only going to cover a very specific task of estimation, which is if we use the sample mean to estimate the true mean of the population, how reliable or how accurate such estimation is. And we do so by construct the so-called confidence interval. So we construct a confidence interval by reinterpret a fact that we have used in the hypothesis testing, which is if sigma is known, then this quantity follows a standard normal distributions. And also we know that the probability of z score falls between these two numbers are associated with 95% chance. And therefore, this is also true, meaning this quantity, this ratio, falls between these two values is also associated with 95% chance. So we move from here to here by multiply both sides with the denominator. And from here to here, we move the x bar to the other side of the inequality. From here to here, we just simply rearrange the terms. But this last equation offers a new insight, which is the following. If we assemble a sample and calculate its sample mean, I can create an interval centered at the sample mean with the width of this term on either side. Remember, this term is a constant because sigma and n are both constants. So I can create an interval centered at the sample mean and then with the width of this quantity on either side. Then that interval will include the true mean of the process with 95% probability, and which is the concept of confidence interval. So if you want to create a confidence interval with a higher confidence than 95%, all you need to do is change this first equation by choosing two other values that would be associated with a higher probability. And by the same algebraic manipulation, you can arrive at a different confidence interval associated with a higher confidence. And so this is the situation where the sigma is known. And similarly, if the sigma is unknown, we can replace sigma with s, which is the sample standard deviation. And since we also know this quantity will now follow a t-distribution with the degree freedom of equal to n-1. So by the exact same logic, we can also construct a confidence interval for mu with desirable confidence. So finally, I am going to give you a very brief overview of many topics on statistical inference that we cannot afford the time to cover in this course. So statistical inference actually is widely used in many applications, such as in drug development to evaluate the effectiveness of different medicines, or in marketing research to evaluate the effectiveness of different type of advertisement, or in a political poster to sense the public sentiments. So there are many special tests developed for different specific situations. However, they are all founded by the similar idea that we have discussed so far. So here I'm listing a few important topics that are covered in a textbook, but will not be covered in this lecture. The first important topic is how do we determine a sufficient sample size to answer questions such as in political polls, can sampling 1,500 people truly reflect the view of a nation? So chapter 8.4 provides a brief discussion on this topic. And in chapter 10, the two-sample hypothesis test is discussed. So for example, if we need to evaluate the effectiveness of a medicine of reducing cholesterol, so one way we can evaluate such effectiveness is by assembling two samples. So we measure one sample which consists of people consists of the cholesterol levels of people without taking this particular medicine in question. And for another sample, we measure the cholesterol levels of people who have taken the medicines. So essentially we have two variables, so that they are called two independent populations because the same person do not appear in both samples. So essentially we are trying to evaluate whether these two density functions are identical to each other. So that is called two-sample t-test, a common method used to evaluate the efficacy of medicines. And a slightly different approach will be, I will use only one sample. So I will measure the cholesterol level for each subject before they have taken the medicines. And then after administering the medicine, I can take another measurement of the same person after they have taken the medicine. And again, I will look at the two associated density functions to see whether or not they are identical to each other. But for both cases, if the two density functions are identical to each other, then we need to conclude that the medicine is not effective. So in chapter 11, the topic of analysis of variance is discussed. The analysis of variance served a similar purpose to the two-sample tests, with the difference of having more than two samples. For example, if we try to evaluate two medicines in their efficacies of reducing cholesterol, then we will need to assemble three samples. The first one will be those people who are without such medicine. The second sample are those who have taken the medicine A. The third sample will be those people who have taken the medicine B. So the goal is to evaluate the density functions among those three variables. So another topic that we will not have time to cover is the hypothesis test on proportion. So all the tests we have discussed so far are for a continuous variable, but we can apply the same idea on discrete variables. And in this case, in the proportion test case, the variable we will study is actually a binary variable. Namely, it will either take on 0 or 1. So if we place it in the setting of evaluate presidential approval rating, then we could use 0 to indicate the approval of the president, and 1 to indicate the disapproval of the president. And then the mean of the variable EX becomes a percentage, which is what the presidential approval ratings is based on. So these are just some topics that we will not have time to cover, but they are nonetheless quite useful and important. So this will conclude our second lecture on statistical inference.